the director of the Research Center of Intelligent Manufacturing and Robotics. And there will be a presentation and then followed by an open discussion. The aim is to help our faculty position themselves and have an idea about the difference. So it is expected from Dr. Samir to show us the kind of mathematics they use in their center, and what is expected in general from affiliates or from especially for mathematicians. The floor is yours, Dr. Samir. Please go ahead.
All right. Assalamu alaikum. Thank you for inviting the center to this meeting. So we are today myself and Dr. Saeed Akhtar, and of course you are a member of the center already, and we might have more, inshallah, in the future. And so thank you for this opportunity. I would like to present maybe just 2 slides, and then Dr. Akhtar will have another presentation, complementary presentation. So let me upload the slides. I hope you can see the slides, yes?
Yeah, we do.
Okay, so I spent a little time to find out how I can communicate with math professors coming from an engineering background. And as you look at the title, it says engineering approach to problem solving with math. So that's the purpose of the meeting. And also, I wanted to make things easier to develop a language that can be understood by both sides, and therefore we can communicate. And therefore, I'm not expecting to see any results in the first or second meeting, but probably later. So the way we solve our mechanical engineering problems is initially assuming that I have a beam that has a length with the square cross section, and I am applying a force at the end of the beam, and it's bending or in the middle, supported by both sides, and therefore we have the solution of the bending. So this is what we call a standard problem with known analytical solutions. Okay, so these are the basic solutions to basic problems. And if we don't have the solution that is not tabulated, because we have, in fact, data books where those analytical solutions are tabulated. And then for the engineer is just to go there and pick up the solution of this beam that is bending towards its tip or in the middle. We could have different situations. And then we use that solution. The solution is the deflection, for example, or if we would like to calculate the stiffness of that beam that is bending. If we don't have a solution, for some reason that table is incomplete, then we have to write the differential equation and then solve it, first order, second order, analytically, and extract the solution. When the problem becomes non-standard, so what does it mean non-standard? It's not tabulated. The shape of the beam is not anymore with a cross-section that is square or rectangular. It may be variable over the length. It can be with a random shape. Okay, so that depends on the problems. And therefore, there is no tabulated solution for this type of beams, if I take these as an example. And therefore, we need a numerical solution. A numerical solution goes through a geometry representation, and therefore I can model that geometry or discretize the problem into finite difference or finite element modeling, because finite element modeling can solve any phenomena irrespective of the shape. Okay, so when we say irrespective, we still have the singularity issues. We still have the convergence time to the solution if the grid is very large, for example, or if it's extremely refined, that takes too long to solve, and so on. We still have those mathematical problems, but I can solve for what I call non-standard. Non-standard means a random geometry, for example, for the time being. Finite element is the first, maybe secondary course, okay, to mechanical engineers, okay. It is a library of elements that have been programmed separately to solve specific issues in traditional fields. And these are almost comprehensive. It takes from structural analysis, deformation, stress analysis, vibration, to heat transfer, to fluid flow, mass transport, electromagnetic potential, etc. So the range of physical problems is large, but the library is not comprehensive. Okay, so a specific number of problems have been programmed into those elements to be able to solve a problem. So it happened that there are issues that we find out, or when we try to come up with a new process, when we design something, when we try to be a little more innovative, combining physical problems together, heat transfer with vibration, for example, and then at the interfaces, we might discover that there are other phenomena that have not been taken into consideration. And therefore, the FEM becomes incomplete. Incomplete in terms it doesn't solve the problem that we are aware of, and therefore we have two solutions. Either we program that element and introduce it to the code, the software. We use ANSYS, Abacus, and so on. Dr. Akhtar will give you more details in his presentation. And or we can solve the problem separately and then combine it. Separately means analytically, okay, just that interfacing problem, and then we bring back the solution back to the finite element global mesh that is solving other issues, okay, and then we solve everything together. I hope Dr. Akhtar will give you a better example. So as engineers, we need to translate the physical problem that we observe into equations, and that's one of the most difficult exercise at the moment. We train our student to observe things and derive equations, simple equations, first order differential equations of small, minor, simple, standard problems. And then through that exercise, we would like to develop that skill to move forward for more complex issues and write the equations to them. But still, this is not an easy exercise, still difficult, because at the moment, the issue is how to combine completely different phenomena together. You have an electro-thermal, elastoplastic problem, and then if I write, I have to make sure that I consider the two phenomena together in that piece of material. And then I'm writing something that is related to heat, to elastic deformation, and possibly vibration, okay? And how to write the links between the differential equations to make sure that the system is comprehensive and may behave altogether without issues. So the question is whether what I'm writing, is it comprehensive really? Is the problem well posed and complete? Is there something missing? This is something we have to look at. But most of the time, to my understanding, okay, or my experience, I'm talking about my experience. I'm not pretending here to have a full coverage, of course. So does it include the model that we write should normally include the geometry and the phenomena variation in space and time. And most of the time we are not sure about this when we solve the problem analytically, because the model in analytical, when posed for analytical solution or solving, is still in the group of the standard problems. When it becomes non-standard, it is an issue. Even some of the papers I have seen from math literature, some of them, the few number I have seen, was always starting from what I put here as a standard. When it becomes non-standard, then it becomes an issue, and I don't think analytical solutions exist. I cannot pretend to say this, but this is the aim, is how to derive those solutions from when the models start to normally to have a variance, okay, in terms of, especially in terms of if geometry or combinations of materials. For example, you have a beam that is composed of two materials, for example. And the other issue is how to translate math answers. So whatever is solved from the mathematical point of view as a result, what does it mean physically? And vice versa. If I have a physical answer, can I translate it into a math equation so I can look at its behavior and effects of other parameters on that response? And this is something that is to me is still a challenge, okay? And that's why math is becoming, I think, very interesting to engineering. Of course, math can still do the research, develop, and fly. And engineering can also do the research and fly. I think they can fly much better if they combine skills. And I see that math is very important to engineering. So here I compiled 3 examples from my experience again, not very comprehensive, of course. And I'm considering here a case with, let me get the laser. So here we have a ball that is in contact on a surface in 2 modes. The first one is that it can actually roll on the surface, but I'm not interested in full rolling. I'm interested in the pre-rolling, which means that it is in a position, and I would like to move it left or right, okay, to see what is the resistance of the material on the ball, okay, how the material will resist that pre-rolling, okay? And therefore, we wanted to determine what could be the pre-rolling friction, for example. So this is at a stable position, and I would like to perturbate it left and right and see how this material can react to that pre-rolling, for example. And therefore, I can write this standard equation that you recognize, but the only material effect will be shown in this term here, okay? And P will depend on the type of material. And therefore, I can derive from here, for example, the torque, okay, MRR here, left and right. So it will start from 0 position to a point and then come back to the next point. So this is moving in a sort of pendulum. Imagine that you have a long bar here. Okay, that's the experiment we do, by the way, to verify the solution. And therefore, the ball will go left and right, okay, within a short period here. You see that we move in between plus minus 100 arc second. An arc second is one out of 3,600 part of a degree. It's something you can not even see. But we measure it with a laser, and we can extract this type of behavior. If I want to do a similar thing in vibration, for example, with the same ball on the same point, and I push it with an harmonic force. So y in this second problem here, this is in y-axis. Y-axis is vertical. Then it's a second order dynamic motion in contact here. Okay, and again, I will show the stiffness of that surface with this term that is almost similar to this one here. Okay, these two work were very independent, and you can see the dates. That was in 1993, while the other one was almost 25, 27 years later. But then that phenomena is almost the same. We're not sure whether, by the way, this is very accurate, and what are the other alternatives to that solution. But for us, the only way we can verify this is through the experiments, okay? And you see, from a mathematician, maybe you would say that it's a weak way of posing the problem. I agree. We don't put all the conditions, or we don't discuss the uniqueness of the solution, and so on. Okay, we have a problem, we make sure that we have the minimum requirement, and then we solve it. This was solved, by the way, numerically. And that one also, I think, Newton Raphson, if I well remember. So what we get here is a very interesting phenomena of nonlinear displacement with respect to frequency. And then we observe something that we could never see in this equation. And that's the difference here between math and engineering. So what is that phenomena is if I move into the frequencies forward, okay, I will have to move from A to B, C, and then at times I will jump to it happens that here the ball actually will jump at certain frequency here, okay, it will lose the contact, okay, and go up to a certain height, okay, and then as I increase the frequency, then it comes down and continue normally. If I do the reverse frequency, I will not come back to the same point here, but I will continue, and then I push. In fact, I will deform the material a little more. Of course, we're talking about 0.4 micrometer. It's deformation because of that frequency, and then we continue. So that's nonlinear issue. Okay, we would never see that if we did not solve the equation numerically and go and observe it physically. Otherwise, in the solution, whatever you solve here will not be, that part here cannot be seen from the point of view of math, if we say it that way. So there is always a strong relationship between the understanding of the phenomena that can emerge from the problem solving. It's the same thing here, by the way. Here it was, to our understanding, it was the first time that we could solve this type of problem at really nanoscale here, and come up with the resistance to the pre-rolling. Another third problem is the law of propagation of uncertainty at higher orders. What is it? What does it mean? If I do any measurement, then say I calculate the surface of the area of a square. Okay, it will be then the one side squared. Okay, and that is equal to the surface. So what is the uncertainty I make on the surface? That uncertainty will depend on the uncertainty of the side A, for example. So it depends how I measure that A. It will affect the uncertainty of calculation of S. And I can imagine that I can have multiple parameters to calculate the volume. It becomes then 3. If I calculate the mass, then I add the density. And every time I add a parameter, I affect the uncertainty. And that uncertainty that I measure for one length, for example, can be of first order. For example, that is, I calculate the surface that will depend on the uncertainty of one length. But that length can vary over time, okay, for whatever reason. And that becomes then the second order uncertainty that, by the way, nobody considers this in real measurement in standard scale. But if we start to do nanometrology, okay, then it becomes very important. And even with it, that second order, I could have a third order variation, okay, here. And we wanted to see what could be the effect if I develop that uncertainty towards maybe the second order or third order here for just one variable. Then I can calculate this uncertainty through this equation here, where fx is the PDF. And then I can develop to the second order. So my uncertainty now on the first order, this is what I can measure every day. Then when it becomes second order, is something I cannot measure with what I have today. And I can move to the third order. So here on the second and third order, this is where if you design any mechanical system that is of extremely high precision, you are designing it to the first order. But if you would like to make it more perfect and evaluate the uncertainty, the other uncertainties of higher orders, that we have to move to the second and third order. And these needs lengthy mathematical development of that uncertainty for one variable. So far, I can have two variables. I need two components that measure, that compose the measurement, and so on. And then later, we would like to find out now the problem is on the engineering. What is the technique that can help me to identify the second order uncertainty or third order or fourth order, and how big is it? I can say that up to the third order, maybe it becomes not necessarily not very important, for example, in practice. And then I limit my development up to, say, second order here. No need to move because all that development is becoming very not very practical. So I don't want to take too much time. I will stop here. We can possibly listen to Dr. Said and then have a discussion after that.
Thank you very much, Dr. Samir. The floor is yours, Dr. Sohail. Dr. Sayed.
Yeah, thank you, Professor Dattar. If you allow me, would like to share my slides. Well, Professor Samir has opened up very nicely. I mean, and I guess he made my life a bit easier in discussing things. I mean, I'm not going to get into the details of complex mathematical equations, or I just want to talk about our research activities, current ones, and the possible collaboration with the math professors today, inshallah. Mostly, I mean, in our mechanical engineering department, most of the faculty members involved in numerical and analytical techniques. Like myself, I worked in different areas, and today I will talk about the activities which are related to the center. I mean, because the center is intelligent manufacturing, so I will mostly talk about manufacturing processes, not others. Numerical techniques, when we talk about numerical techniques, of course, as Professor Makid mentioned, that mostly we are working with numerical techniques like finite element method, finite difference, finite volume, and others, or combinations of all these techniques using different softwares. Mostly we use Abacus, ANSYS, COMSOL, or some other dedicated softwares, for example, Advantage for machining applications, and others like Deform for large deformation, metal forming processes, for example. We also use some analytical tools like my group, for example. We have developed some predictive tools where we can use mean field homogenization techniques to predict the properties of heterogeneous materials, for example, or we also worked on analytical tools to simulate the flow behavior, for example, or to design our heat exchanger, and so on. So for this particular purpose, we use MATLAB and other softwares like equation solvers, softwares. We are also using somehow like statistical techniques like regression modeling, design of experiments, sensitivity analysis, reliability, maintenance, and so on. Since because of the time limitation, I would not go into the details, but I would just focus on the numerical and probably the analytical techniques. So as already discussed, what is finite element? Okay, so of course for us, finite element method is the most common one, where we capture the deformation behavior and capture the stresses during deformation. For example, if a manufacturing process involves deformation, a process can involve thermal fields like welding, for example, or machining, or coupled with structural problems, fluid flows, for example, and we can have the coupled problems like solids and fluids and so on. Of course, our approach is a bit different from mathematics. I mean, like department mostly. I mean, if I'm not wrong, so as Professor Makid explained that mostly we are dealing with complex problems. Like physical problem is complex. Most engineering problems are complex in nature, and we cannot most of the time cannot get the exact solution for that particular problem. So we have to have numerical approach where we approximate our solution by discretizing the problem into small elements, and of course, as you know, the elements. Like for example, for structural problem, the stiffness matrix is solved for each element, and we get the global stiffness matrix after solving the whole problem. So the scenario is simple. How we solve our problem. We have a physical problem. The problem can be a welding problem. It can be a fluid problem. It can be, let's say, a casting problem. And always each problem is governed by equation, either differential or even integral equations. And we convert the differential equation, for example, into algebraic equations considering the elements and so on, and we get the finite element solution, we get the results. Of course, always we are encountering errors when we solve the problem, so we have to refine the analysis by improving the mathematical modeling, and also we change the physical, the physics of the problem, for example, the boundary conditions and so on. So we usually optimize our problem by iterative kind of approach, but mostly we are going to validate our solutions with experimental data. So this is probably the main interesting thing with us. We always try to validate our results by having some experimental data. We're not going to the much details, just to give you some glimpses of the real manufacturing processes or some structural applications. In mechanical engineering, for example, we always deal with complex problems. You can see, like, these are a few of the examples, like crushing analysis or fluid flow through channels, or like implants under loading, human body, and so on. So when we solve our problem, always we go from simple assumptions to the more complex situation, and we are our purpose is to capture the real natural phenomena of the problem. Mostly engineering problems are non-linear in nature, of course, as you know. So we have to have to capture the non-linearity. Just to give you some practical examples or fields which we can apply in the finite element analysis, and what are the expected outcomes or outputs in our analysis are, for example, if you are dealing with static analysis, so mostly we are dealing with deflection, stresses, strains, forces, energies, for example. If it is a dynamic analysis, so we are going to capture the frequencies and the modal analysis, like more shapes, for example, and so on. If it's a heat transfer analysis, we are interested in the temperature gradients, for example, heat fluxes, and so on. If it's a fluid problem, so we have to have like pressures and other things. In fact, no single problem is having only single phenomena in engineering. Mostly we are dealing with multi-physics problems. For example, some problems, simple problems, usually mathematicians deal is, for example, only structural problem, where they talk about the stress analysis, the buckling, for example, or vibration. If it is a non-structural, for example, a thermal or fluid, for example, so we can solve them separately. But in fact, in real manufacturing and applications, as the center is focused on, is the multi-physics problems, where we are having combination of different physics, like thermal structural problem or fluid structural problem, and so on. The manufacturing process is going to have mostly all the phenomena, even the thermal, the phase change phenomena, the structural diffusion even. So I will go into the little details after a couple of slides, but just to give you some idea of what is non-linearity in our problems. And mostly, if you look at the sources of non-linearity, always we have, the mathematicians would be more interested in the the non-linearities. Like we have for structural problems, always when we talk about the stress and strains, we talk about the constitutive equations. We have in a structure, we have the body forces, the traction forces, where the equilibrium equations play their role. and the relationship between the strains and the displacements, we call them kinematic equations. Now, for example, if we have a nonlinearity can exist between stress and strain, we call it materials nonlinearity. If there is a nonlinearity occurs between, let's say, the kinematic equations and equilibrium equations, these are the mostly we call geometric nonlinearity, or even others are possible. We have contact problems, as Dr. Like Samir gave in his speech. So we can have contact problems which is a boundary condition nonlinearity. Let's say rolling of a ball on a certain surface, or like let's say you are going to pull something, let's say a nut, okay, from the bolt, for example, or riveting. So these are all contact problems. Moving of, let's say, car tire on the road is a contact problem. So it's a non-linear contact boundary problem, and so on. Of course, we have equilibrium equations, constitutive equations, and so on. If you just talk about only the material nonlinearities, I mean, mostly some of the faculty members I know, they are working on material nonlinearity, where the material behavior is important. In let's say in manufacturing, when we manufacture something, it means we are going to play with the materials. Material can be metals, where we can assume rate-independent plasticity, for example, or rate-dependent plasticity. Material can be viscoplastic. Creep phenomena could be there. We can have gasket materials. We can have rubbers, viscoelastic, for example, for polymers or polymer composites. We can have so many, different materials possible, and we can design our own materials where the built-in library of the softwares are not feasible. So we can have our own subroutines. We can have our own user-defined materials by writing some codings. So all we play with these things in our mechanical engineering fields usually most of the time. Of course, this is just a quick overview of what we are doing. We don't have time to get into the details. But I will just give you some examples from our research, current or past research projects. Just to give you, a few examples from laser-assisted manufacturing processes. It can be surface treatment. It can be machining, like laser drilling, for example. It can be welding, for example, like laser welding. So our, research team here are, teams are working in these areas, for example, where different physics are involved, like heating, and the thermal stresses because of the temperature gradients that can occur in the laser processing. Diffusion is also there, for example, if you talk about the laser process. So we have a laser beam with nitrogen, where we can use this heat source for welding or cutting or other purposes. So when we talk about the heat transfer problem, for example, it deals with the Fourier heat transfer equation. Of course, it's a moving heat source, so it's not that straightforward. We have a heat source or source term in this equation. We have, this is a standard Fourier equation, but with the energy which is absorbed by the substrate material. At the same time, this energy is a function of the velocity or the speed of the laser source. Here, let me take the laser pointer here, because we are talking about the laser. So we can see that we have the velocity term, okay, and this, the specific heat, how to solve the, so basically we solve this equation to capture the temperature gradients in the substrate. Then we can have, of course, a coupled problem, like say diffusion, how the nitrogen diffuses, for example, into this substrate. It can be steel, it can be other material. And this is basically the fixed equation, fixed law with, I would say, modified fixed law, where the substrate is also dealing with the non-uniform solubility when the nitrogen comes into the substrate and get into and diffused. Of course, diffusion is an important phenomena in engineering applications, which is a temperature and time dependent phenomena. Of course, structural problem, the stresses are always occurring. I don't know how to run the simulation. I just wanted to show you some simulation results. For example, we can simulate and get the stresses. We can have the temperature gradients, and then we also conduct experiments to validate our results. And of course, we can play with different parameters of the laser to optimize our surface, our cutting quality, and so on. The second example I'm taking is based on the application of phase field modeling, which we have applied to different applications like thermal barrier coatings. We can also apply this to gas nitriding. We have applied it. We can also use the same phase field modeling to casting problem, which is an important manufacturing process. Of course, again, it's a multi-physics problem. This is something like coating means that if you talk about the real application of coatings in the kingdom, we have turbine blades. The blades are coated with TBC, thermal barrier coatings, to protect the blades and extend its life. So mostly the failures occur at the top coat. So what happens when the crude oil which we use makes some let's say salts like vanadium oxide, and these salts get into the blade surface, and how the structure changes and how the structure change will create cracks in the top coat of the blade. So we call them transformation induced failures. So it is not that straightforward. It involves diffusion of the melt into the substrate, which is a ceramic based, and then there is a transformation of the substrate material, which is ceramic. Like it transforms from tetragon to monoclinic structure, and the volume changes there, so it cracks. And then the related thing is the stresses that appear into the surface. So now, how to deal with these? Of course, I mean, the governing equations are there for each phenomena. We are combining diffusion with the transformation with the stress equations, and we solve the equations in couple mode, applying of course the real boundary conditions. We solve them numerically and get the, of course it's an iterative process where we can optimize our blade. Okay, for example, how the salt diffuses and changes are occurring into the surface. Those who are interested in this, of course, I can send the papers to them, or they can get the paper for it. It's one of the papers we have published in collaboration with, of course, this work was done in collaboration with one of the projects with MIT. Metal forming is an important manufacturing process. We also worked on the nitriding, which is the heat treatment process. If you talk about the extrusion process, we get extruded products. Okay, there are so many good applications of extrusion. For example, the window frames, which is made from aluminum. How we get them? By extruding the aluminum billets through extruder, and the dies are, or which is the tool to extrude these billets into useful products. Now, the life of the die is important. This is an example how we can extend the life of the die, which is a tool. Usually these dies are subjected to heat, surface heat treatment, okay, or we call them, let's say, nitriding or carbonitriding. So we can simulate this diffusion phenomena as well. We have worked a lot in this area just to focus on enhancing the reliability of the die by extending its in-service life. Of course, we always, as I mentioned earlier, that we always validate our results. Let's say the case hardening by diffusion process. We can check how can we control the diffusion layer. So we work in this area as well. I think this is an interesting work where we have used hybrid computational approach to simulate the coating process, where we are, for the first time, we have captured the residual stresses in the coating by simulating the real process of the coating, where we have used three techniques, like statistical modeling to get the real parameters in the coating process in collaboration with Toronto University in Canada. We got the the parameters from there where they use for them, and then we have simulated the deposition of the droplets in the process using the point cloud approach. We call them smooth particle hydrodynamics, where we can couple it with the finite element model. So for the first time, this is done, and then we can simulate the process of the droplets. Of course, we worked on the multiple droplets as a real process to capture the residual stresses in the process and the cracks. So playing with the parameters, our purpose, of course, is to decrease the residual stresses, enhance the quality of the coatings. This is the purpose. So we have used coupled approach. We call them hybrid computational approach to capture this phenomena or to simulate this process. Of course, there are three kinds of governing equations involved: the Navier-Stokes equation, okay, to solve the deposition, and then of course the thermal, the Fourier equations, and then for structural problem we have used the standard stress equilibrium equations. Those who are interested in the mathematical treatment of this, we can discuss it later, or at least they can visit the paper to get into the details of the equations. Because of the time limitations, I would not be able to show them here. Of course, this was something about the finite element modeling, but we also worked in the mean field homogenization as well as computation homogenization, where we have developed some tools to predict the properties of heterogeneous materials. I mean, we have so many applications of composite materials. We call them like polymer-based composites, or like ceramic-based composites or metal-based composites. So our team here have used the analytical approaches to build some codes to predict the properties. Of course, these properties are based on well-established and extended, okay, solving of equations. Like, for example, for thermal properties, we have used Maxwell equations, and then we have modified those fundamental equations to bring more innovations, like to capture the effect of different attributes like the particle size in the composites, the interface resistance, the shape, the aspect ratio effect, and so on. So, of course, we don't have time to get into those details, but those who are interested in the, in the analytical studies of the prediction of properties for heterogeneous materials, they can visit these papers which we have. I mean, these are some of the papers we have recently published. This is one of the latest paper on the new differential scheme, which we have published for the polymer composites, which can deal with the non-dilute filler concentration. Most of the fundamental equations available or approaches available to capture the, let's say, thermal conductivity of composite is based on the dilute concentration, but we have modified those models and applied for the non-dilute concentration. This is the most important, I think, achievement by our group so far. This is just the last slide. I mean, if you allow me, Professor Tatar, just to give you a complete picture of what we are doing here. I mean, from manufacturing point of view, from analytical tools. For example, our product is the cutting tool, which is used in machining application. So this is, we usually use tools to cut a certain product by machine, but the tool itself is an important, component in in this particular manufacturing process. So we have used three approaches: how to design the material. For example, it's a composite material, heterogeneous material, so we can design our material first. We can get the optimum tailored properties using our built predictive models. And then we go to the lab, we make these inserts by different powder metallurgy or other techniques, we develop them. And then we can simulate them using finite elements, okay? And then we can test these developed tools in real manufacturing process. The purpose is to optimize the process, to reduce the machining time, to increase the quality of the product, And of course, we are now in the intelligent manufacturing, so we are going to extend now this approach to have this process more smarter and more intelligent by embedding some sensing and sensors and so on. So I would stop my lecture. Sorry, not lecture. I'm sorry. My presentation here. Of course, we have some other slides, but I would not like to talk about these right now. If you have, any questions about my presentation, though it was not that comprehensive, but I tried my best to put all things together. Thank you very much.
Thank you, Dr. Syed Suhaib Akhtar. Thank you very much, Dr. Samir. You were straight to the point. You have showed us the different models used in your research, the different techniques, and so on. We have a few minutes for questions, but I believe that you have already answered many of what was expected as questions. So let me go to the audience. The floor is yours. Any question? By the way, we have Dr. Ahmed Bonfou, who's expert in Cahn-Hilliard equations, since you are interested in Dr. Syed. Dr. Ahmed, can you say something about Cahn-Hilliard equations? Ahmed Bonfou?
Yes. Assalamu alaikum.
This is one of the most used equation in the work of Dr. Akhtar, I think.
Yeah. So yes, of course, I have been working on this model, Cahn-Hilliard equation, with many applications. Even nowadays, we have much more applications like tumor growth. There are many other applications of this equation, for this Cahn-Hilliard equation, but especially in material science. So phase change, separation of phase, etc. Yes, I have been working on this equation for some time already. Yeah, so we will see what we can do together. We'll discuss later. Yeah.
Yeah, Dr. Ahmed is working rather on well-posedness and existence of attractors and descriptions of attractors, I think.
Yeah. The solutions, yes. So we try to first prove theoretical accurate solution, theoretical solutions. Then there are many applications, simulations of this using finite element, etc. But mostly, I'm expert in proving the well-posedness. I'm not a numerician, but more on the theoretical side, the well-posedness, etc., the property of the solutions, the last time behavior of the solutions, all these things, yes. But together we can work with numeration, they can do simulations, etc.
Yeah. Dr. Qasim, anything to say about numerical treatments, finite element methods, and so on? Dr. Khalid?
Assalamu alaikum. Thank you so much for the presentation. It is very interesting. I just want to ask about finite elements. Did you choose finite element because of the existing softwares? And because of its convenience in applying it on complex geometries? Because I think engineers, they always talk about or raise concerns about finite elements, the conservativity property. Finite elements, it's not a conservative method. So for this reason, many engineers in industry, maybe I'm not right, they choose to work on finite differences and finite volume method because they are conservative. And the other thing, I know in nonlinear materials, or sometimes you may need to deal with high order finite elements to capture the details of nonlinearity, and also you need to work on a very fine mesh. Thank you so much.
Thank you, Dr. Qasim. Any comment, Dr. Samir, Dr. Akhtar, Dr. Sayyid?
Yeah, sure. Actually, Dr. Samir, do you want to comment first?
Just sentence. By definition, finite element was never accepted by engineers or even by math people, because it defies one of the issues that you just explained. But the problem, the positive thing is that we can get a solution, and that solution is not exact, of course, but it has a delta error that engineers can accept. And it is still a very useful, like you said, approach to solving difficult problems. Yeah, yes, Said.
Yeah, of course. Actually, particularly if I would say, for solid mechanics problems, we usually deal with the finite element. And if you talk about the finite difference, of course, mostly simple problems. Okay, with regular CAD geometries, they are solved by finite difference method. But when we talk about complex problems, like you need complex in geometrical nature. When we have irregular CAD geometries, we usually have problems in solving through the finite difference techniques. If you talk about the finite volume, of course, finite volume is not used for solids. They are mostly used for the fluid mechanics, and most of the CFD softwares that are based on finite volume method. Because we are dealing with volumes of fluids. So for continuum mechanics approach, mostly we are using finite element method, and it is something more common in engineering. Even we have multiple courses in mechanical engineering where we just focus on finite element method.
Yeah, Dr. Qasim.
Thank you so much.
Dr. Manal, any question? Does your research fit in this?
Thank you so much.
Okay. Any other question, Dr. Rashid, Dr. Saeed, Dr. Shahzad? Any question? Dr. Jafar, Dr. Sulaiman, Dr. Muhammad?
I think Dr. Munir Bhatt has raised his hand.
Yeah.
Thank you very much for the nice presentation. Actually, I am working on the Stokes control problem and the Navier-Stokes control problem, which fits in the flow problem in your talk. So is there a possibility, or is there any group working on the control problems with reference to these flow problems? So you
Sure, because actually, yeah, you are right. As I mentioned, when we talk about any manufacturing process, and we talk about, let's say, the deposition of, let's say, a liquid onto some surface, for example, like in the 3D printing problem, for example, we have this phenomena, droplets form, and they strike, for example, a certain surface, and then the liquid solidifies into solid. So this is a multi-physics or kind of problem where we are dealing with fluid interaction with solid, and it solidifies. A phase change problem, like entropy method, can be used, and then because of the thermal gradients, we have these stresses. So yes. We don't deal with the fluids as an isolated phenomena, but we deal with a kind of multi-physics problem where we can couple all these equations together. Actually, our purpose of presenting today is that we are not mathematicians. We need to get your expertise in improving our existing models, and of course we rely on the built-in equations solver in softwares like COMSOL, Abacus have solvers, and these softwares are built on equations. And sometimes we feel difficulty in understanding the equations. So I think this is the right avenue for us to collaborate on these problems. Of course, we can use Navier-Stokes equation, other fluid-based phenomena like casting, deposition, or like heat exchanger problems where we have a fluid flow in the pipes, where there is, so there are so many good applications where we can collaborate.
Okay, thank you. So I will share you some of the papers through your email, and if you find it related to your field, then please let me know. Okay, thank you.
Inshallah.
Thank you, Dr. Said. I very much liked your explanation. It was very clear, yes, where mathematicians can interfere. Dr. Khaled, do you have something to say?
Okay. Colleagues covered most of the things. There is one side, I don't know if also can be explored. Nowadays, they are talking about data-driven models where you don't have let's say, the full boundary conditions given or the full initial conditions given, all what is available, some measurements here and there, and one can try to construct the solution or recover the parameters of the equations, of course, through kind of neural networks or machine learning. So this approach, considered now, tackling the issues in the center?
Dr. Samir, can I?
Yes. Yeah. Okay. Go ahead. Say.
Yeah. Of course. Very, very, very. Good question. Actually, we are dealing with data. Of course, we have run some sensitivity analysis based on some data analysis. We have always in any engineering problem we are dealing with data. We can go with the ANN modeling or other design, or like the Guji experimentation, like strategies to predict the behavior or to optimize our responses. So we are dealing with multi-objective problems in engineering. For example, if I give you an example of nitriding, for example, I have published, for example, one paper on nitriding where we have taken into consideration different process parameters. And these process parameters can be temperature, it can be pressure, it can be the time. And how can these parameters affect the response? Now, response can be the hardness of the nitrided layer which we are getting from the process. Now, based on the data we are collecting, by optimizing our process, we can get optimized results. So we do with the ANN or training, or we are also now, one of our faculties working on the machine learning, which we can use to predict our responses based on the data we are getting. So yes, we can have experimental data, we can have virtual experimental data where we can run some simulation models to vary our parameters to get the response, and we can use that data to train our model. So yes, very good question. We can work in this area as well.
Yes, one of the applications we have in our plan is to work on haptic tools, which means that, for example, you have a cutting tool in a CNC machine, and you have a part, okay, but that part, you don't know the material, you don't know the composition of that material, and hence you don't know what is the process, the parameters of that process that should be defined to go ahead with the machining, for example. And that haptic tool, which means an intelligent tool that will touch the part initially, do a first surface cut, for example, and then from that data, he will determine what are the mechanical properties, and therefore immediately define the parametric process to be used. That's one of the applications. The second application that we have in our portfolio is related to stability of any mechanical structure. We've been discussing this for, I think, last 3 months, where, for example, you have a robot that should stand in an equilibrium position. And if there is any perturbation from whatever source, he should be able to come back to his stability position, and therefore there must be a machine learning out of those behaviors and know where to come back, because you cannot program everything in a robot, and therefore those algorithms based on data or sometimes large data are of great importance.
Thank you, Dr. Samir. Thank you very much, all of you. We will certainly schedule other meetings. Most probably, there will be a kind of workshop in the reporting period, where we will invite our faculty to show you, to present their works, the problems they are working on, the techniques used, the analysis, the arguments, and also their skills, so that you can you can judge, you can decide on the possible applications to your fields. Thank you again. Thank you very much, and have a good day. Thank you, Dr. Saeed. Thank you, Samir.
Okay, thank you very much.
Thank you.
Assalamu alaikum.
Thank you very much for
Have a good day.
your invitation. Assalamu alaikum.